Hello everyone. I'm Masumura from Machine Vision Lighting Incorporated, Japan. Today, I will be covering the second half of the overview of a series of episodes on the visa method, which is the origin of lighting and imaging technology essential for the visual function of machines, and which we learns the essence of light in the object. This time, I will introduce the overview of the second and the subsequent episode of the seven-part series, Visa Method Writing. First, let's look at the essence and approach of the Visa method in the second episode. As already explained, VISA stands for Variable Irradiation Solid Angle. When light is irradiated onto an object surface, scattered light is usually returned, which appears to be the same brightness from either direction. That would be fine, but in reality, direct light that seems to have been directly reflected by a mirror is also returned. This means that the brightness changes depending on the viewing direction. If you look from a direction where no direct light is returned, it will be completely dark. However, the brightness will only be that of the scattered light. In fact, most objects, which are general objects, retain this direct light and scattered light in a certain ratio. This means that if you cannot quantitatively capture this direct light, you cannot quantitatively capture the brightness of the object surface. In other words, you cannot obtain a quantitative image. As the title says, the radiation solid angle is the angle range from which the light is radiated onto the each points of the object. This radiation solid angle is stored as the solid angle of direct light, so the brightness of this point is determined by the observation solid angle and the angle range at which it is observed or captured. This is called the factor of solid angle. And with the Visa method, this factor of solid angle can be made uniform at any point on the object surface. It is now possible to quantitatively capture the change in propagation direction, which is one of the four changes elements of light. This was not possible until now. Therefore, with conventional lighting, it was not possible to obtain quantitative images. However, if this becomes possible, it will be possible to obtain quantitative images of other wavelengths, amplitude, vibration, and other information. So since it has not been possible to obtain quantitative image up until now, people have been working hard to introduce AI systems. But in fact, by incorporating conventional rule-based image processing, it has become possible for machines to perform extremely accurate visual recognition. The third episode is about the basics of the Visa method. With conventional lighting, if P1 and P2 on the surface of the object are different, if the location are different, the irradiation solid angle, that is, the irradiation condition, will change. Scattered light from object is proportional to illuminance. If the illuminance of P1 and P2 are almost the same, a business card, my business card, that emits scattered light will look uniform. Well, it looks almost uniform. But if you place a mirror that only reflects or emits direct light on this, you won't be able to see anything at all. This is not like looking at the surface of the mirror. The image becomes as if you were looking at the ceiling and the ceiling light source. By contrast, if you use the Visa method to make the radiation solid angle the same at every point, the shiny metal from earlier will look like paper. You can easily get quantitative images. This is the edge of mirror, and this is the scratch. If you change the content of the radiation solid angle to concentric RGB cycles, a flat surface will be blue, and if it is indented, you can change the RGB ratio. This is a scratch in a dent. If you make it radial RGB, you can see in which direction and how much it is tilted. In other words, you can get complete 3D information quantitatively. If you put these together, you can see that even subtle bending, large dents, and even tiny scratches and chips are accurately reproduced. If you zoom in, you can see that there is a scratch inside the dent. Next, in the fourth episode, we will introduce the effects and application of the Visa method. This is a used coin, and with conventional lighting, even if the image appears to be beautiful at first glance, in fact, this was not quantitative. But with the Visa method, you can simply radiate it with Visa lighting, with the same lens and the camera, and you can easily get a quantitative image. This is a tablet that is quite difficult to inspect. But when you take a picture of it with Visa lighting, you get an extremely uniform quantitative images. So the bulges and the dent in the number 1 properly reflected in this image, there are. In fact, it may look like an image with low contrast, but this is characteristic of quantitative image data. To take an extreme example, if there is even a difference of just one tone, in a place where the same one tone should be different, it will look like there is a difference of just one tone. Therefore, it is possible to image everything from the curvature of this tablet to the dent in the number 1, or even defects, chips, scratches, and things like that in one shot. If you apply this to semiconductor wafers, you can easily to crystal defects that were not visible before. This is the convex part of the mirror mentioned earlier, but it seems that the crystal grain boundaries are slightly misaligned to form the convex part. This is an image that can only be seen with an electron microscope, but it is possible to observe it in real time. Next, as the 5th episode, I will introduce a new approach of Visa method. This is a diagram showing the resolution of the Visa method. The horizontal resolution is the pixel size divided by the lens magnification, and the depth resolution is multiplied by the tangent of the tilt angle per gradation of the object surface. If you reduce both the irradiation solid angle and the observation solid angle, the resolution in the depth direction increases. However, If you increase it too much, if the subject tilts even a little, then the object light cannot be captured, so it becomes invisible. In addition, there is a diffraction limit. So, the ultra-thin concentric irradiation solid angle is truly a magical light that mankind has now acquired. For example, we can now irradiation any point on the object surface with what might be called the ultimate ring lighting, where light and dark alternate with the difference of just zero point 0.1 degrees. This means that even if it is flat or tilted, the same information can be obtained if the angle changes in the same. If you tilt it, the direct light that is returned also tilts, and this is the interaction and relative relationship with the observation solid angle, and the light and dark are repeated until the direct light can no longer be captured. If you take a picture of a mirror with this, it will look like this. In this example, the theoretical depth resolution is 0.86 nanometer. It's amazing. Areas of continuous brightness with the same brightness have the same tilt. This is a differential image. After all, they are not the same height. They have the same tilt. We can quantitatively image that adjacent area of the same brightness have a difference in inclination of just 0.8 degrees. Using this, for example, this red part, a cross-section, we can determine the degree of inclination on the pixel by pixel basis using only the light and dark information, and by connecting these together, we can determine the 3D shape. In the 6th episode, we will discuss the future development of the Bezier method. Right now, we are trying to incorporate Bezier lighting into various lenses. This is a Bezier lighting with a 3 magnification telecentric lens. And if you use ultra-thin concentric stripes irradiation solid angle with this, normally this resolution is 78 picometer at depth. This is sufficient, but this is theoretical. It means that the theoretical resolution can be brought up to 98 femtometers. This is also a normal resolution, but this is actually for a 5 mega camera, and the pixel size is 3.45 micron square, and this resolution can be obtained by only 3 magnification. The other is a wide field of view. This is a 0.11 magnification telecentric lens. But even with this, if you use an ultra-thin concentric stripes radiation solid angle, you can increase the resolution to a range of several hundred picometers, which is sufficient, and I think it is sufficient to see even normal defects in semiconductors, such as crystal defects. The 7th episode is the final episode on the new horizons opened by the Bezier method. As we have explained so far, Bezier lighting is lighting that overturns the conventional wisdom of lighting by simply shining light onto an object using this Bezier lighting in one shot with a normal camera. A wide field of view of up to diameter of 100 millimeters can be achieved. and in terms of depth resolution up to a theoretical resolution exceeding nanometers. Of course, this can be made rougher or even down to millimeters, and this can be obtained as a quantitative image that can be restored in 3D. This means that can provide accurate teaching data for AI systems, or it can provide accurate images for rule-based image processing. Also, what's more, it has the feature that 3D information can be visualized in real time even during visual inspection. Another thing is that visual lighting is, in fact, a small imaging laboratory that allows for quantitative experimental verification of the imaging conditions of the lighting system and optical system. With one visual lighting system, you can quantitatively verify what kind of lighting would be used with conventional lighting, at what distance, what kind of image would be obtained from what angle, and how the target defects would work. It's truly a small imaging laboratory. What's more, this can be directly transferred to lighting equipment for mass production. That's all for the 7th episode. I've given you a brief overview of the PISA method, which is the basics of the very basics of all imaging technology. Thank you very much.